Okay, in this lecture we want to do some discussions of noise. So first of all, let's go back and review the meaning of the term decibels. dB or decibels are units that compare the intensity of two signals using logarithmic ratios. So it's not really a unit, but it's just a logarithmic scaling of a dimensionless ratio. So in other words, if I take volts over volts, I get a unitless number. The reason we even use decibel is to indicate that we've done a transformation into the logarithmic scale. Now, why would you want to use decibels or dB instead of a straight ratio? Well, first, when you do a log operation, it compresses the range of values. So in other words, a range of 1 to 1000 becomes a range of 1 to 3 in logarithmic scale. Second, when numbers or ratios are multiplied, they can be added if they're in log units, and this is particularly useful if you're graphing. So if you come from an electrical engineering background, you probably did Bode plots, and the reason that Bode plots can be additive of functions is that you've taken the logarithmic of several ratios. And then finally, the logarithmic characteristic is similar to human perception. So we're able to perceive over orders of magnitude in both visual and hearing. When we see the visual spectrum, we're looking at orders of magnitude of frequency. When we listen to an auditory signal, we're listening to orders of magnitude in frequency as well. So it gives you a similar characteristic. So by definition, originally unit was used called the bell, which didn't have practical application. So it was replaced by the decibel, which is 1/10 of a bell. When it's defined only in terms of a ratio, dB units are used to talk about power or intensity of a signal. So if we're talking power, then dB for a ratio of powers is 10 times the log of power 2 over power 1. Now, I was actually almost hesitant to even show this slide because this is typically not the ratio that we look at, because we're typically not talking powers when we talk dB and signal to noise ratio. We're typically talking voltages. So because the voltage is proportional, or because power is proportional to voltage squared, you can see in that previous equation, if you substitute voltage squared, then remember the log of a quantity squared is 2 times the log of that quantity. So the 2 comes out front and we end up with 20 log times the voltage of signal 1 over the voltage of signal 2. It's possible to just talk about voltage in dB for a single signal, in which case you can see that you just take 20 times the log of V of the signal. So basically it's 20 log of signal 1 over signal 2. So the signal to noise ratio then is just the ratio of signal to noise, and that's measured in RMS, or root mean squared amplitude. So if you have not reviewed root mean square, it was shown in the previous slide. You need to go back and be sure you understand the difference of what RMS means. Remember that we use RMS to represent something like an equivalent DC voltage that would give us the same power. So it's a common term in electrical engineering, but it's also used anytime you have signals that have time variation. So the signal to noise ratio is expressed in dB typically, and so basically you take 20 times the log of the RMS signal voltage over the RMS noise voltage. Now if you want a straight ratio, so if you want a signal to noise ratio that is not in dB, then basically you can convert this by raising everything to the power of 10. So you would have 10 to whatever the signal to noise ratio was in dB over 20, and then that will just give you a linear signal to noise ratio. So for example, and you can plug some numbers in, 20 dB means that the signal RMS is 10 times the noise RMS. 3 dB would be a ratio of 1.414. And I will point out that in these slides here, this 20 over 20 is actually an exponent. It's not multiplied. This 3 over 20 is an exponent. It's not multiplied. These slides come from come from your textbook publisher, and I have noticed as I've gone through that there are some errors. So if you're watching this video, here where it says minus 3 dB means that the ratio is 1 over 1.4. That would be 10 to the power 1 over 1.4. So basically they're plugging in right here for this dB number. So if I tell you you have a signal to noise ratio of negative 20 dB, then you would plug in minus 20 right here, and that would give you 10 to the minus 1, which would be 1/10, which is what they're saying down here in the bottom line of this example. So here's some examples of actual data. This is a sinusoidal waveform, and the first graph shows a signal to noise ratio of 10 dB, and then the noise increasingly gets larger and larger until this final graph down here on the bottom right has a signal to noise ratio of minus 10 dB, meaning the noise is an order of magnitude greater than the signal. So you can see that by the time you get to minus 10 dB, you really can't distinguish the original waveform. Minus 3 dB, maybe you can see a little bit of that sinusoidal oscillation, but you certainly wouldn't be able to distinguish any kind of frequency or anything like that. So really, you need to be at the ratio of 3 dB or higher to really distinguish your signal visually from the noise. So what is noise, and where does it come from? Well, basically noise is what you don't want, and signal is what you do want. So noise is some kind of unwanted variability of the signal, and often noise will limit how useful the signal is or what kind of information content you can get out of the signal. So talking a little bit about noise, and particularly we'll talk about noise in biomedical signals. One of the biggest sources is a physiological variable. So an example of this might be if I were acquiring your EEG. Sometimes EEG probes pick up heartbeat, and so you'll see superimposed over the EEG a heartbeat signal, which is a signal that you don't want. So even though technically it's not a random kind of noise, it is a signal that appears in your measurement that you don't want. So we characterize it as noise. One potential remedy is to just modify your overall approach. In other words, use a different kind of measurement technique. Maybe place your probes in a different region. Maybe use some kind of active electronic system that will do noise cancellation, possibly a differential measurement. So you can actually change your measurement. Sometimes that's not possible, and in that case then we are going to use techniques of signal processing to remove signals like that. And primarily we would use independent component analysis to do that. So when we get to that section of the lectures, I'll remind you of this. Environmental noise is another kind of noise that can be internal or external. This would be sources of similar energy form. This would also be, for example, if you had breathing going on when you were trying to measure heart rate, here's where your noise cancellation can come in. These two, physiological and environmental, are very similar. In the physiological variability, your measurement would be sort of indirectly related to the variable of interest, and it's easier to think of concrete examples when you think about internal. And these divisions here are just, and really all of these divisions are just semantics. An artifact means the transducer responds to other energy sources. The classic one that we use in biomedical signal processing is when you are measuring a brainwave, the eye movements are considered an artifact. And so they show up very clearly on your EEG, but they're very hard to get rid of because they often share a common frequency space. So that would be an example of an artifact in a signal. And then finally, electronic noise, which is thermal noise or shot noise, and that comes from the transducer or electronic design. Basically, the theory here is that whenever you use anything electronic, you're typically using a silicon semiconductor type device. There is a certain, once those devices get above the temperature of absolute zero, there is a certain electronic noise associated with them. So variability is really noise, but the word's often used to indicate fluctuation between measurements as opposed to within a measurement. So that would mean if you took a heart rate several times and looked at sort of the difference in the measurement, that would be variability. If you look, say, for example, at you were looking at someone's gait pattern and you were measuring time between steps, you would measure each step, but if you treated each step measurement as independent, then there would be variability within the measurement. If you took measurements of that on several different occasions, then there would be variability between the measurements. So a lot of signal processing tools exist to reduce noise. Ones that you've probably been exposed to are basically filtering, and that's very useful for things like electronic noise or known frequency noise sources like 60 hertz. There are some others that we will talk about this semester. The more you know about the characteristics of the noise, the easier it is to apply the different signal processing methods. So noise is generally considered to be a random variable, and because of that, describing it as a function of time is not particularly useful. The one exception might be if you had something that was very repetitive, like a heartbeat or something that you could clearly define. But typically, common problems used to discuss noise include their probability distribution, its variance, and its spectrum. So noise can take on a variety of different probability distributions, but the central limit theorem implies that most noise is going to have a Gaussian or a normal distribution. So the central limit theorem is a very important theorem, and it basically says that if we have a large number of independent sources of noise, it will have a Gaussian probability distribution that is independent of the probability distribution of the independent sources. So here is an example of what we just stated. So in the top left corner here, we're just looking at some random numbers distributed between 0 and 1. And then the y-axis here is the probability that you will generate that particular number. So this is called a uniform distribution because it means that any number between 0 and 1, we have roughly an equal probability. And this is just one random number generation. So after one random number generation, if we were to plot the random numbers as opposed to their values between 0 and 1, it might look something like this. Now, if we do that twice and we average that, then basically what happens is the shape of that function changes. So this rough looking line in figure B would be if we took two random distributions from figure A and averaged them together. And note that now our distribution is no longer uniform. We actually have a peak at 0.5, the mean between 0 and 1. Now this dashed line here is a Gaussian distribution given by the following function where sigma is the variance. So if you then take more and more averages, you notice that the rough looking curve becomes smoother and smoother. And by the time you've averaged 6 of these uniform distributions, then your curve is starting to look very much like your Gaussian distribution. So as an example, you can use MATLAB to generate a Gaussian distribution and determine the probability distribution. You can also estimate the distribution of the data produced by the RAND function, which gives you a uniform distribution. So basically a histogram is a tabulation over a data set of the number of occurrences of a given range of values. And so if you have a value that falls within a given range, it's stored in a bin associated with that range. So let's say, for example, our range is from 1 to 10, and we have 1,000 numbers that are generated between 1 and 10. Then we might set one bin to be between 0 and 1, and then all the numbers that fall between 0 and 1 would be counted, and that value would be plotted in the bin between 0 and 1. So how many bins to use is usually user defined, and then histograms are plotted as counts against the range with the value on the horizontal axis and the counts on the vertical axis. You can do that in MATLAB easily by using the routine hist. The data vector is x. New bins is the number of bins that you desire, so you can even set this up in a loop where you vary the number of bins and see what the histogram looks like. The output stored in a histogram vector and a vector x out that gives you the mean of the ranges for the bins used, and then you can plot that. So this is an example of some code that would take a 2,000 point data set of randomly distributed values, and then in this case we're a 20,000 point data set. So we're setting 20,000 points, we're setting 40 bins. This is our random number generation that would generate random Gaussian noise. And then this is our histogram calculation. The histogram is then normalized to 1, which doesn't necessarily have to be done, but it's useful sometimes when you're comparing different distributions in different data sets. It's useful to normalize. And then plot it as a bar graph. So here's the result when the random n function, the Gaussian distribution function, is used and the number of bins is set to be equal to 40. You can see that here we get this distribution. It's approaching that smooth Gaussian, but of course it won't get there until we have an infinite number of points. And then here is our uniform distribution, where we have roughly uniform distribution between 0 and 1. So both of those generate histograms. This is very useful for looking at whether or not your data set forms a normal distribution. So many times when you are looking at statistical measures, so this is sort of the end game. You do all the signal processing on a biomedical signal, and then you look at statistical measures to try to determine whether or not you've got anything that is statistically meaningful for either diagnosis or identification of a group or identification of a phenomenon. Like, say you're trying to predict a seizure. If you've got some feature that shows up that accurately, you think accurately signifies a seizure is about to happen, then you would begin to do some statistical calculations to determine whether that's significant effect or not. In doing that, it's much easier to do if your data have a Gaussian distribution. So plotting a histogram of your data points can sometimes tell you if the distribution is Gaussian or normal, and then that determines what kind of statistics you use. So just to go back once again and review, this random n function generates a Gaussian distribution. If we leave out the n, that would just generate a uniform distribution. This calculates a histogram. This normalizes a histogram, and then this line plots that as a bar graph. So histograms useful in looking at data. So that's all we're going to discuss in this particular section. There is a section in your textbook on electronic noise and the generation of electronic noise. That's more of a topic. It's a useful topic. We'll go ahead and look just really briefly. Basically, the electronic noise is present any time you're making a measurement, and you have sensors, physical sensors and transducers that make the measurement. So it's specified typically over a bandwidth or range of frequency. It's characterized as being a roughly uniform distribution because it basically it's called white noise, and that just means it has effectively a flat distribution across all frequencies. When you obviously are working with signals, you're going to do some filtering, so there will only be a range of frequencies that you'll be concerned with, so you can model your electronic noise as just being uniform across that range of frequencies. And then of course you need to know something about what is the power level of that noise or the voltage level of that noise so that you have some idea of how to model it. So like I said, we're not going to go into depth in this because this is really more of a topic for a biomedical instrumentation course. But basically that noise voltage is related to Boltzmann's constant, the temperature in Kelvin, and the resistance in ohms. And so then that'll give you a voltage due to your electronic noise, which is also known as Johnson noise or thermal noise, because it happens when you have sources that are resistive, and this noise is generated due to oscillations of the electrons in the material. So basically that's what the electronic noise is. So that's going to end then this lecture on